Something is sitting in the darkest part of the observable universe. It is not a star. It is not a galaxy. It is not anything that should be there according to every model of physics we have built over the last 100 years. James Webb looked into a region of space so empty that astronomers had effectively ignored it for decades. And what it found did not just surprise the scientific community, it quietly terrified them. Not because it was violent, not because it was dangerous, but because it was impossible. And the universe is not supposed to contain impossible things. This is not a story about a beautiful discovery. This is a story about a signal that does not fit, a presence in the darkness that should not exist, an object, or perhaps something larger than an object, hiding in a region so cold, so remote, so featureless that no telescope before Webb had ever looked closely enough to realize something was wrong. And now that we have looked, the question that follows is deeply unsettling. How many more are out there, hiding in the dark, in places we never thought to examine? To understand why this discovery is so disturbing, you first have to understand what the darkest regions of the universe are supposed to be. Astronomers divide the sky into zones. There are regions crowded with galaxies, clusters, filaments of matter stretching across cosmic distances. There are voids, enormous stretches of space where very little matter appears to gather. And then there are the deepest voids, places where even the faint background population of distant galaxies seems to thin out. These regions were not mysteries. They were simply the spaces between structures, empty by definition, quiet by expectation, not worth extended observation because, according to our best models of large-scale cosmic structure, there was nothing significant to find. Webb found something significant. The region in question sits in one of the statistically emptiest patches of sky accessible to the telescope. When Webb turned its golden mirror toward this patch as part of a deep field survey, scientists expected background galaxies, faint and ancient, smeared across the infrared spectrum. They expected noise and uniformity. They expected the familiar texture of a universe that had been thoroughly mapped and mostly understood. What they found instead was a structure, a concentration, a signature in the infrared data that did not belong to anything in the surrounding field. Not a nearby object, not an artifact of the instrument. Something real, something distant, and something that immediately forced scientists to confront a question they were not prepared to answer. What kind of object can be that massive, that cold, and that invisible, sitting in a region of space where almost nothing should be? The answer begins with what Webb actually detected, and this requires understanding how the telescope reads darkness. Webb does not see light the way human eyes do. It operates primarily in near-infrared and mid-infrared wavelengths, between approximately 0.6 and 28 micrometers. This range allows it to do something no previous space telescope could do with the same precision. It can detect objects so cold they emit almost no visible light. It can see through dust that blocks optical telescopes completely. And it can observe light from galaxies so distant that the expansion of the universe has stretched their original ultraviolet and visible emission all the way into infrared wavelengths by the time it reaches us. When Webb scanned this dark region, the signal it detected was not a bright point. It was a diffuse infrared excess, a region where the background radiation was slightly but consistently elevated compared to what the surrounding field predicted. Not a flash, not a dramatic spike. A quiet, persistent glow, barely above the noise floor, spread across an area larger than most astronomers were comfortable dismissing as instrumental error. That kind of signal has a short list of explanations, and none of them are reassuring. The first possibility is that Webb detected an extraordinarily massive, cold cloud of gas and dust on a cosmic scale that has no equivalent in any well-studied region of space. Molecular clouds exist throughout galaxies. They are the birthplaces of stars. They are cold, they absorb visible light, and they glow faintly in infrared. But those clouds exist inside galaxies. They are embedded in structure. A cloud of comparable or greater scale floating in a deep void, detached from any visible galaxy, would represent something that our current models of cosmic structure formation do not produce naturally. Gas does not gather that way in empty space without a reason, and the reason is always gravity, which means if the cloud is real, something massive enough to hold it together must also be there, even if we cannot see it directly. The second possibility is more troubling. What Webb may have detected is the infrared signature of a structure sometimes called a dark galaxy. This is not a science fiction concept. It is a genuine theoretical prediction that has been debated in the astronomical community for years. A dark galaxy would be a gravitationally bound system, a true galaxy in terms of mass, but one that failed to convert its gas into stars at the rate normal galaxies did. It may have been disrupted early in cosmic history. It may be composed mostly of dark matter with only a sparse population of stars, too faint and too few to register in optical surveys. It would be nearly invisible to ordinary telescopes, but its gas, compressed slightly by its own gravity and heated faintly by background radiation and whatever stars remain inside it, might glow just barely enough in infrared for Webb to detect. If this is what Webb found, then it is the first observational candidate for a class of object that has been theorized but never confirmed. A galaxy-sized system, sitting in a deep void, invisible to every telescope that came before, detected for the first time only because Webb's infrared sensitivity pushed past the threshold of what had previously been measurable. That would be one of the most consequential astronomical discoveries in decades. But there is a third possibility, and it is the one that has generated the most serious scientific concern, because the infrared signal detected by Webb is not uniform. Within the diffuse glow, there is a region of subtle but detectable gravitational lensing. Background objects near the edge of the structure appear slightly distorted. Not dramatically, not in the way a massive galaxy cluster bends light into bright arcs. Subtly, quietly, in a way that only becomes visible after careful mathematical analysis of the image data. And gravitational lensing requires mass. Lots of it. More than the faint infrared signal alone can account for. That discrepancy between the amount of matter visible in infrared and the amount of mass required to produce the observed lensing effect is the detail that shifts this from a puzzling observation into something that genuinely challenges the standard model of cosmology. The simplest explanation for that discrepancy is dark matter. An enormous concentration of dark matter, not associated with any visible galaxy or known structure, sitting in a void where large-scale structure models do not predict significant mass concentrations. Dark matter halos are supposed to cluster around galaxies. They are supposed to follow the cosmic web, the filaments and nodes that trace the distribution of ordinary matter through space. A massive, dark matter concentration floating in a deep void, with only the faintest infrared signature as a companion, would mean that dark matter can gather in ways our simulations do not reproduce. It would mean the cosmic web has hidden nodes we have not accounted for. It would mean the universe contains more invisible architecture than our best models predict. And it would mean that the voids we thought were empty are not. They are not the spaces between structures. Some of them may be structures themselves, dark and cold and massive, lurking between the bright things we have always focused on. The implications cascade outward from there in a way that is difficult to overstate. If dark matter can concentrate in voids independently of visible matter, then the large-scale structure of the universe is not fully described by the galaxies we can see. Our maps of cosmic structure, built from decades of galaxy surveys, may be fundamentally incomplete. The Sloan Digital Sky Survey, the 2DF Galaxy Redshift Survey, the ongoing DESI survey, all of these map the universe by tracing luminous matter. But if significant concentrations of mass exist in the voids between filaments, invisible to optical and even radio surveys, then those maps are missing an entire layer of the cosmic architecture. And that missing layer may be gravitationally significant. It may be influencing the growth of structures nearby. It may be shaping the paths of galaxies across distances we have never suspected were connected. There is also the possibility that what Webb found is something older than any of these explanations suggest. The earliest universe was not smooth. In the first fractions of a second after the Big Bang, quantum fluctuations created density variations in the primordial plasma. Most of those fluctuations grew into the galaxies and clusters we see today. But some theoretical models predict that certain fluctuations could have evolved differently, collapsing into configurations that are massive and gravitationally coherent but permanently dim. Not black holes in the traditional sense. Not galaxies in the ordinary sense. Something between. A primordial dark structure, a relic of the earliest instabilities in the universe, surviving billions of years without ever producing enough light to be detected by any telescope that existed before Webb. If that is what this signal represents, then James Webb may have found a direct observational connection to the physics of the universe's first moments. A fossil from the time before stars. A remnant of a process that astronomers have modeled mathematically but never seen in the data. And that word, terrifying, which sits in the title of this story, is not chosen for drama. It is chosen because of what it implies about our understanding. Science is not only thrilling when it confirms what we predict. It is thrilling and unsettling and deeply humbling when it finds something that sits outside every prediction we had confidence in. The terrifying part is not the object itself. The terrifying part is the question it opens. If this structure exists in one of the darkest, most ignored regions of the sky, and Webb found it almost by accident during a general deep field survey, then how many more are there? How many voids that we have classified as empty are actually occupied by dark, cold, massive structures that our previous instruments were simply too limited to detect? How much of the universe is hiding not in the distant past, not at the edge of the observable cosmos, but in the nearby dark, in the regions we looked at and decided were blank? This is the moment in astronomy that changes the direction of future research. Every observation Webb makes of this structure will generate new questions for theorists. Every measurement of the lensing distortion will constrain the mass distribution of whatever is there. Every comparison between the infrared signal and the predictions of dark matter simulations will either support or challenge the models we have built over 4 decades. And if the data continues to resist explanation by known physics, if the mass implied by the lensing is too large, the temperature too cold, the position too isolated for any standard model to accommodate, then scientists will be forced to do the hardest thing in science. Revise the foundations. James Webb was built to see the unseeable. It was built to look past the dust, past the redshift, past the thermal noise, into the parts of the universe that older instruments could not reach. And it has done that magnificently, in galaxy after galaxy, in stellar nursery after stellar nursery, in black hole after black hole. But this discovery is different, because this time, Webb did not find a clearer view of something we already suspected was there. It found something in a place we had decided was not worth looking at, something the models did not put there, something that sat quietly in the void for billions of years, invisible, massive, and patient, waiting for an instrument sensitive enough to notice that the darkness was not entirely dark. The universe has never been as empty as we thought. Every generation of astronomy has learned this the hard way. Every time we built a better instrument, the voids filled with detail. The blank sky became crowded. The silent frequencies became loud. The invisible became visible. And every time, the lesson was the same. We had been missing more than we knew. We had been calling things empty that were only empty to us, only empty to our limited instruments, only empty according to our incomplete models. Now Webb has looked into the darkest part of the universe with the most sensitive infrared eyes humanity has ever built. And the darkness looked back. Not with a flash, not with a violent outburst, but with a quiet, persistent signal that refused to be noise, a faint structure in a void that should have been featureless, a gravitational distortion in a region that should have had nothing to distort, a presence, cold and enormous, hiding in the space between the things we thought we understood. This is what the universe does. It waits. It lets us build our models and draw our maps and fill our textbooks with confident explanations. And then, in the quietest corner of the darkest region of the sky, it shows us something that does not fit, not to threaten us, not to disprove everything we know, but to remind us that the map is never finished, that the darkness is never truly empty, that the most important discoveries do not always arrive with brightness and fanfare. Sometimes they arrive as a whisper, a faint infrared glow, a subtle curve in the background light, a signal so quiet that only the most powerful telescope ever built could hear it. And now that we have heard it, the question is not what it means for one observation. The question is what it means for everything we thought we knew about the universe. Because if something that massive can hide that well, in a region we ignored for decades, then the true structure of the cosmos is still largely unknown. And Webb has only just begun to look. What terrifies scientists is not the darkness itself. It is the growing realization that the darkness has always been full. We just never had the eyes to see it until now. Think about that. And if you want to understand what else Webb is finding in the places we never thought to look, the story does not end here. The universe is not finished revealing what it hid, and neither is this telescope.